All right, welcome to part 2 of today's lecture. So we're going to be talking about sound. So in the last video, we introduced two types of waves, transverse and longitudinal. We spent some time looking at transverse waves and how mathematically we're supposed to represent those, but we don't actually need that pretty much ever for sound. Sound has its own set of equations that we would need to use if we get into sound design. It's got some other stuff that you have to deal with. So let's just ignore that wave equation and let's talk about sound as the longitudinal wave that it is. So it turns out sound doesn't just travel through air. We know sound travels through air because we live in a place that has air and you have heard something before. Right? That's just how this works out. However, sound doesn't just travel through air. If you watch older movies, I guess they don't necessarily have to be older movies, but if you watch movies that occur when the United States was expanding westward, or you watch, kind of older style war movies, a lot of times people will take their head and they'll press their ear to the ground. It's because they're listening for sound that's traveling through the ground instead. Well, so it turns out sound requires a medium to pass through. It's never going to pass through just, it can't travel through vacuum. It can't travel through space. That's something else that we would have to look at. That's not sound. We need a signal of some type, which we'll technically talk about in the next video. So sound travels through some medium. That medium's not always air. We're going to primarily focus on fluids for what sound is traveling through. So that's going to be gases and liquids. We're not going to be getting into solids because that involves a little bit more understanding on how solids are structured and so forth, and the textbook doesn't get into that. The textbook does just focus on fluids in this case. So this is an example for how sound works out. So here we have a loudspeaker, and all these little points are air molecules of some type. And so with the loudspeaker, what's going to happen is inside you have something that's going to be moving up and down with whatever it's putting out sound-wise. When the inside of the speaker pushes outwards, it's going to compress the air molecules. And when it moves inwards, it's going to create what's referred to as a rarefaction, where you have less air molecules. And that's going to be pushed away from the source, which in this case is the speaker. We'll see an animated version of this in 2 slides from now. But basically what's happening is the air molecules themselves aren't moving. They're just going side to side some amount, whatever that amount happens to be. And when we are looking at these compressed areas, there's a higher pressure. There are more atoms there that result in a larger force at that particular location. A rarefaction, you would have lower pressure because you have less molecules. No, it's on this slide, not the next one. My bad. But here's an animated version of it. I know this is a little hard to look at, and the loop is not perfect, but let's focus on the wave. So this particular column is the wave. The air molecules inside of this are not the same. There are a couple of molecules here that are simulated that are red. They're moving back and forth. They're not moving with the wave. So these kind of chunks that you can see moving to the side, those are compression areas, and the middle section between them are the refraction areas. So this is what a sound wave would look like if it was akin to a simple harmonic motion thing. So if you hit like a tuning fork, for example, and it plays the same note, this is what the air could be simulated as. So at room temperature, sound has a very specific speed in which it travels. It's 343 meters per second. It's pretty fast. Air molecules are arranged in the air in such a way that they can move really easily. So when you generate pressure with your mouth, that's going to be able to propagate through the air quickly. Now, this is not going to always be the sound or the speed of sound, right? This is for air at a very specific temperature. It's what you should use unless you were going to be given something else. If you have another temperature, you would need to go through and use this equation. But we're not going to be calculating this. Instead, I just want to talk about how the speed of sound is different depending on what it travels through. So here we have air at two different temperatures. Helium, again, a gas. Ethyl alcohol, a liquid. Water, a liquid. So all of these, it's pretty fast. Sound travels quickly. But when we get into solids, so granite being a rock and aluminum being a metal, the speed of sound is really, really fast. So in those movies, the reason they stick their head to the ground is you would be able to hear through the ground. They could be further away because sound is traveling faster than if you were waiting to hear them through the air. So this is a little bit into sound. Again, we're not going to get super into it because you're pretty much going to cover everything you need for sound next semester over the course of maybe a day max. There's not a ton of sound done in this particular physics sequence. Even in upper division physics, I don't think we ever really talked about sound again. So it does lean a lot more towards an engineering subject where you use sound engineering to help design locations to amplify or reduce sound. So we are going to leave the additional sound stuff for Physics 130 for you guys. All right, so that's going to be it for this video. Make sure to watch the last video, which is based on light.